3 prisoners were sentenced to death. One of them French, one of them German, one of them British. What is your last wish? They ask the French guy. He says, a bottle of exquisite French wine. What is your last wish? They ask the German guy. He says, I want to give a speech. What is your last wish? They ask the British guy. He says, I want to get shot before the German starts his speech. Unfortunately for you guys, it is too late now. This is my name. This is how to pronounce my name. And I'm working on machine learning and learning robots and artificial intelligence at the Swiss AI lab, ICIA, in Lugano. And I also have a group of researchers working in the robot learning group in Munich. The field of general AI, AGI, artificial general intelligence, is currently, I believe, in a transition phase from a collection of heuristics towards a real formal science with optimality theorems for universal problem solvers living in arbitrary environments where they have to maximize their reward and their user-defined goals that they have to achieve in an optimal fashion. And it turns out there are mathematically optimal ways of decision-making in unknown environments of a very broad type. And all of this is good because heuristics, they come and go, but theorems, they are for eternity. And to illustrate that, 2 years after I was born, Good speculated about superintelligences, informal speculations about what a superintelligence might do if it improves itself and then becomes an even smarter superintelligence that can improve itself even in an even more amazing and better way. And this inspired me to formalize this notion of self-improvement. And it turns out there is an optimal way of improving yourself if you are an AI that is able to rewrite its own code. And that's the Gödel machine. The Gödel machine, which is named after Kurt Gödel, whose self-reference trick I'm using to build such a machine. Kurt Gödel is the founder of theoretical computer science because what he did in 1931 was to write down a universal programming language using the integers. And he showed the limits of mathematics and computation by encoding in that programming language a universal proof-generating or theorem-proving system. And he was able to devise self-referential formulas in this language that talk about themselves, and they say, for example, I am not provable by a computational theorem proving procedure. And by doing that, he had a theorem or a statement, a mathematical statement, which either was a true theorem, but then it was not provable, or it was provable, but then it was false, and so mathematics would be flawed in a fundamental way. Gödel was an Austrian. He did this work in Vienna, but later he emigrated to the United States, just like another great Austrian thinker who then became governor of California. We use this self-reference trick as follows. We take a standard computer like this one, and we load it with a special type of software. The software contains some initial program for interacting with the world, and it's a suboptimal way of maximizing reward there in the world according to some user-defined utility function. In addition to that initial piece of software, there is also a proof searcher in the initial software, which systematically, in a certain optimal way, asymptotically optimal way, is generating proofs until it finds a pair of a program and a proof that shows that if you apply that program to the initial software such that it becomes a different type of software, such that you rewrite the original code of the machine, then afterwards the performance of the machine will be better than before. And if you think about that for a while, any self-rewrite that the self-improving machine is going to execute will be globally optimal in the sense that it's not worth waiting for the proof searcher to come up with an even better program that is corresponding to an even better self-rewrite of the Gödel machine, because the proof already must recursively take into account that the effect of the current self-rewrite on all the possible future things, future self-rewrites that it is setting the stage for. So, in a certain sense, this is a theoretically optimal self-improver. However, before this first self-rewrite, what can we do to make it already very impressive before it has found a way of improving itself for the first time? And one answer is we can initialize it with an algorithm that every computer scientist should know, and those who are not computer scientists should at least know that there exists something like that. There is something called the asymptotically optimal fastest algorithm for solving any arbitrary computational problem that you give to the machine. It's due to my former postdoc, Markus Hutter, who did this at the ETH in Switzerland, but now he's a professor in Australia. And this algorithm is going to take any arbitrary computational problem that you give it, and it's going to solve it as quickly as the unknown fastest algorithm for solving that type of problem. Say for a small constant factor, 1.001, nothing, plus an additive constant, which does not depend on the problem size, which means that as the problem size gets bigger and bigger, for example, as you're trying to solve a factoring problem, an integer factoring problem, which is important for e-commerce, cryptography, and things like that, as the problems you're trying to solve get larger and larger, this additional overhead is just constant. It vanishes totally. All right, so let it be known there is such a method, and the only reason why not everybody is using it at the moment is because within this universe there are most of the typical problems are really, really small. They are so small that the constant, the additive constant, still plays a role. And so before the first self-rewrite of a self-improver, what else can we do if it has only a very limited number of instructions per second, maybe 10 trillion, which might be close to what your brain can execute? It's probably an upper bound of what your brain can do. And I don't have a complete answer for that, but otherwise I wouldn't even be here, I guess. However, I think this answer is a partial answer which is going to be important. Let the machine spend some of the instructions not only on solving these external user-defined goals, which often are really hard to solve if the machine is still learning and doesn't know how to do the most basic things. Like, for example, suppose you have a robot and whenever the battery is low, you want to find the charging station. And maybe it doesn't even know how to turn the wheels and all these things. So in that case, it's very unlikely that just through random exploration you are going to stumble across this action sequence that is going to lead you to the charging station. Now, instead, what you should do is generate lots of tiny little self-generated tasks, which are much easier than those given to you by the user, and which have the property that they just increase your knowledge about what you can do and in the world, such that you become a more and more general practical problem solver. So that would be some sort of active unsupervised learning where the goal is to come up with with a more and more sophisticated problem solver that can solve more and more self-generated tasks, where each of these self-generated tasks has the property that it teaches the learning system something about how the world works and what you can achieve in the world. And it turns out that a very convenient way of phrasing that is this thing which I call the formal theory of fun and creativity. In the framework of reinforcement learning, how many people in this room know what that is, reinforcement learning? All right, so almost everybody. You have a utility function and you try to maximize your future expected reward according to this reward function. And normally what you are focusing on is this external reward, which is whenever your battery is low and you reach the charging station, then you get an external reward just for filling up the battery again, or you get negative reward for bumping against an obstacle. And these are just numbers that you add, and the expected future value of all these numbers, that is what you want to maximize. And any problem can be formulated in this framework. So that is the standard thing, the external reward that everybody is looking at in reinforcement learning. However, then there is also this intrinsic reward, this extra thing, which corresponds to the self-generated tasks, not to the user-defined tasks, but to the self-generated tasks. And this intrinsic thing, this intrinsic fun, the intrinsic reward, that corresponds to what humans do all the time when they are, for example, listening to music, because it's somehow intrinsically rewarding to do this. Or when they go to the museum, which also may be intrinsically rewarding, although it's not really relevant, or it doesn't really seem relevant for achieving your goals in the external world. Or for conducting science. Science is about generating actions that lead to data, experimental data, that have some regularity that you didn't know yet. So whenever you come up with an experiment that leads to data that has a regularity that you don't know yet, then we want to translate that into a measurable form of intrinsic reward. And that's what we are going to do. And I believe, and I want to convince you, that the same little thing which I'm going to describe, this very simple principle, is not only explaining science and scientific exploration, but also art and humor. All of music and of science and of art is about patterns that are novel. We have lots of patterns in the environment. The interesting ones, the ones that we want to study more closely, are those where there's some novelty involved, something that we didn't know yet. And we want to make this precise, formally precise, such that we can implement it on robots. And to do this, we have to answer two questions. First of all, what exactly is a pattern? And what exactly does it mean to be novel? And a pattern in computer science is just something where the raw data takes so many bits, but it is patternful because there's actually a shorter program that computes the entire raw data. Because there are symmetries or all kinds of regularities in the data that you can use to more compactly encode the entire data. Random data, white noise, is not compressible, but anything that has a pattern is compressible. For example, this piece of broccoli, which is fractal, because every little detail of this broccoli looks rather like the whole, which means that the same piece of code that you use to encode the outline of this piece of broccoli can also be reused to compute these little details, which means you can greatly compress this image of a broccoli. So that would be one of many, many, many regular patterns, and the world is full of them. But many of them I already know, so these are not interesting. I'm interested only in the novel patterns, those where I can discover a regularity that I didn't know before. So what I have to do is I have to study how many computational resources do I need to encode this data that comes in from the environment via my sensors before learning and after learning. So if there's a difference between the encoding of the data, which first, using my existing compressor, takes so many bits, and afterwards, after learning, when I studied the data a little bit and suddenly, hey, see, there are regularities which I didn't know, which allow me to further compress, then there's a difference between before and after, which means I discovered a regularity that I can measure in terms of bits, ignoring computation time for the moment, but there's a very natural way of adding computation time as well. So the progress that you are making while you are discovering a regularity that you didn't know can be measured. And this regularity can appear in all kinds of data that's streaming in, like music, for example. A new piece of music that you didn't know, which has regularity, like all music has lots of regularities and repetitions, etc., is compressible. But suddenly there's a new chord sequence that in this way never was used before. And that's what makes it interesting, because there suddenly your learning algorithm kicks in and improves a little bit the encoding of this piece of music. And there you're making progress. And this additional, the number of saved bits here, that's proportional to your intrinsic reward. So if you are a composer of music or a listener, then you tend to generate self-generated tasks which lead to data that has this property that you still can discover something in them which you didn't know. And this can be very easily formulated in terms of compression progress, bits that you're saving. And if you're saying your brains is using neurons and not bits, then think of neurons, number of computational resources that you need to use the existing data, the incoming data, before you discover a new regularity and afterwards. So if afterwards you need less synapses and less neurons than before to encode this new piece of music or scientific data because you found a law in the data, then you made progress and you can measure that. It's clear that one can just count these savings. And that's your intrinsic reward. And there are a million ways of getting this intrinsic reward in a regular environment like ours. So here I'm just repeating what I said. And this is, if you want, the central slide of the whole talk. You take some data X, which can be an input sequence, like a piece of music, or some data that you get as you're learning a new motor skill, like juggling. So you have a sequence of actions and inputs corresponding to oranges that you are juggling there. And if you never did that before, then this will be a novel pattern for you, which has properties that are regular, so it has a regularity in there, but you didn't ever experience those before, which means your compressor, your learning machine, has a chance to more compactly encode the thing, which means you have an intrinsic motivation now to learn new motor skills or to compose new music that somehow has a regularity that is new, relative to yourself, at least. And hopefully even to others, which means you might be able to sell it, but this is then related to external reward. You know? So we are just counting the bits that we need to encode the incoming data X. Any part of the sensory action stream can be this X. And the observer at time t has a certain limited way of encoding the incoming data. And then it will need so many bits to do this. And we can count them. And then the essential thing is, as the learning algorithm is kicking in and is looking at this new piece of data and is reducing the number of bits from so many bits to so many bits, you are saving this. And that's your intrinsic reward. In other words, that's your reward for solving the self-generated tasks that you just solved. All right. So there's a continuous time formulation of this, but I won't even go into details. Those who like continuous time, to those it is obvious, and others, they already know the basic principles and can imagine that this is possible. Let me now just apply this whole thing and generate a piece of art a piece of low complexity art generated by a process that is described by this formal theory of fun and creativity that I'm trying to explain. We start with a pattern, and everybody immediately sees that as a well-known pattern, and you understand the rules, how it was created with circles of identical size. And we add 4 times as many circles of half the size, and 8 times as many circles of a quarter of the size, and so on. And we get more and more circles, and there are a few large circles and many small circles. And now we are going to create an artwork which has the property that it can be encoded by very, very few bits of information if you know this regularity. Because what I'm going to do is I'm going to remove most of these lines and just leave a few which correspond to something that humans know. And here is the sketch of that. So here you see a butterfly approaching a vase with a flower. And in the background, you see all kinds of green circles which are not used. But then there are these red circles which are the only ones that are used to specify the sketch. And each segment of this drawing here can be encoded by 3 circles. Now, if I manage to come up with some reasonable drawing that can be defined by few large circles, then I will just need a couple of small numbers, and it will be very compact. And in fact, this is what's happening here. So just few circles are used to encode the whole thing, which means that this final low complexity artwork that I made for you here has a very compact representation. And it fulfills this thing that many artists have, of course, promoted over the centuries and millennia, namely art should somehow extract the essential of the objects that you're depicting. So minimal art is just a most extreme form of this, but any artist is trying to extract simple things from the environment, and with a few lines, with a compactly encodable way, tries to depict the essence of the thing he wants to depict. It takes a long, long time to come up with any reasonable encoding of this type here, but it's also very rewarding as you are going through all these. You need hundreds and thousands of trials to come up with something that looks reasonable, but you get very excited because there's this intrinsic reward whenever you, as an artist, suddenly come up with a new regularity that you yourself were not aware of, but suddenly recognize as this regularity, which you then can use to complete your drawing. A very similar drawing in the same artistic style is this here. It's the same artistic style because it's using the same basic principles for encoding, which means that both of these drawings together can be more compactly encoded than just one of them plus the other one. And to make you see again that this drawing here can be encoded by very, very few bits of information, a very short computer program, I'm superimposing the explanation, which is this. So only these green circles here are used to define every little segment that you see. Every little tiny part of this drawing can be encoded as a sequence of 3 circles. And since I'm using just a tiny fraction of the possible circles, and since I'm greatly limited to using just a few elements here, and not the entire pixel set that might be possible if I did random drawings, I can, or you will immediately see that this is very compactly encodable. So here's the original sketch. Again, the same story. It takes thousands of trials to come up with something that looks reasonable. Most of these things look horrible. But suddenly you discover something that works, and it's really exciting. So after many frustrating trials, you suddenly have this, you solved your self-generated task in a certain sense, and you need to solve a couple of others, and finally you are pleased and say, okay, here my low complexity artwork is finished. So this is just going back and showing again how the basic pattern encoding worked. Of course, there are many other regular patterns. Nobody says you have to take these circles. For example, most of my slides are just composed according to recursive applications of the harmonic proportion, the golden ratio, which is another way of imposing regularities on these things that I'm making on these slides in this case, which again allows to greatly compress the entire thing. You know, before I came here, I thought this is going to be just another small, tiny intelligence conference, and there won't be much of an audience, but you are actually a large audience by my standards. The other day, I gave a talk, and there was just a single person in the audience. A young lady. I said, young lady, it's very embarrassing, but apparently today I'm going to give this talk just for you. And she said, okay, but please hurry. I got to clean up here. So what is it about jokes? Jokes totally fit this principle that I just explained to you. Every joke has this punchline. A joke is a story with a punchline, and as you are listening to it, you need, using your current compressor, if you don't know the joke already, you need so many bits to encode it. But every punchline is designed to be quickly encodable with respect to the previous part of the story. So once you think a little bit about the punchline, just 3 seconds or something is usually enough, you see, hey, it's in an unexpected way related to the first part of the story, which means I suddenly can just introduce a couple of pointers going back to the first part of the story, which means I can save bits, because the extra bits that are needed because of the unexpected punchline suddenly are not needed anymore, which means my original compressor, which knows something about stories, but not this particular story, took so many bits. The raw data took so many bits. My current compressor needs so many bits. After learning, within a couple of seconds, you need so many bits. That's what you save. You count the number of bits. That's the fun that you have. So that's how you have to. That's what you have to do if you want to build machines that can experience fun. You just have to encode things, and you can use that. You can use neural networks if you want, instead of machines that encode in plain bits like this computer here. You just need to have a computational resource, and before the learning happened, you need so many computational resources, and afterwards you need less, and the difference, that's what you're saving. Your lazy brain likes to save things, and that's the fun. And so all you need is this additional reinforcement learner, which not only takes the standard reward, but also this intrinsic reward that you get through discovery of new regularities in science, art, and jokes, to generate actions that lead to more experiences of this type. Many people don't know that the Queen of England is also interested in artificial intelligence. And recently I had the great honor to give a scientific talk, very much like this one, to the Queen of England herself. At least she said that she is the Queen of England. What she said was, if you are a scientist, then I'm the Queen of England. So if we want to build an artificial scientist or an artist, then we need 2 things. We need the compressor, or the predictor, which is the same thing. Prediction and compression is the same thing almost, because everything that you can predict, you can also compress, because you do not have to store it extra. So the predictor needs so many bits. And then afterwards it needs so many bits, and you can count the improvements of the predictor, but then you need the additional machine, the reward maximizer, which takes the improvements of the predictor or compressor as an input, as a reward. And then you have a standard reward maximizing algorithm as known in reinforcement learning, which you then give the task to optimize this thing. So I'm not specifying much the particular compressor or the particular reinforcement learner, just the general principle. what is the goal that you should solve, or which are the self-generated goals that the system should solve in addition to the external goals. So this is an old thing in many ways, because the first system of this type I implemented 20 years ago. And back then, the compressor and predictor really was just a neural network, which just tried to predict the next thing in a little maze like this, where there are some things that are more predictable and others that are less predictable. And so it likes to go to those places where it can learn regularities that it didn't know yet. And then you can show that this sometimes helps to improve external reward intake as well. As you're learning more and more about the environment, this is often useful to maximize as well your external reward, because the stuff that you're learning, the problem-solving skills that you're learning through exploration, through self-generated tasks, can help you to more easily solve the other tasks, which are the really important ones, like eating 3 times a day. Neural networks are still very useful. In fact, they are becoming more and more useful all the time, because computers get faster and faster. Just a couple of months ago, we used neural networks to break the handwritten digit world recognition in record in a benchmark that everybody's using in this field, where you get lots of images of digits that people wrote while they were addressing letters for the post office, and then you were trying to translate these images into symbols, into digits like 0, 1, and so on. And for a long time, the best methods in this field used to be not so much neural networks, but support vector machines. Does anybody know in this room what is a support vector machine? No? So maybe 20%, something like that. Does anybody know what is an artificial neural network? All right, 40%. Partially overlap. So in the beginning, 20 years ago, during the first neural network renaissance, many people used them for pattern recognition, but then there came a time when support vector machines turned out to be much better. But now there's a second type of neural network renaissance, because if you use deep networks, which have as many layers as what your brain has, about 6, 7, 8 between the retina and the visual cortex back here, then you can suddenly solve lots of interesting vision tasks in a way that outperforms support vector machines and all kinds of other methods. So here are the guys who really did the work: Dan Cherezan and Uli Meyer, and down there my co-director of the CIA, Luca Maria Gambardella, who is famous for his work in swarm intelligence. And the main thing that made this work was that, well, first of all, we used these deep networks, but then we didn't use any of these unsupervised pre-training things that became popular recently. So some of you who know the fashions of neural networks, they may know that recently unsupervised pre-training was a hot topic. However, it turns out to be this is not really necessary. All you need is a deep network and lots of training examples. Not only 50,000 like those in the original training set that you get there, but millions that you get through deformations of the original training data. And then to make it work, because we have so many weights, we have 10, 12 million synapses or connections or weights in our system. To make this work, we have to put all of this on graphics cards, which makes everything 50 times faster than traditional CPUs. And that's how we were able to get the best performance so far on this particular benchmark data set. Here's another application of neural networks. Each of these little robots has a little neural network on board that is trying to predict what happens if I send this motor signal to my wheels. And then you can use these predictions, once they are halfway reliable, to plan ahead, tick, 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 and then you still can optimize the action sequences in order to achieve certain sub-goals, like, for example, approaching this ball quickly without bumping it away or without bumping into an opponent or something like that, breaking in time. And this is Alexander Gloy-Förster. He was the leader. He's the leader of my current robot lab, and he also was the leader of the 2004 team. These are videos from the 2004 World Championship in the Fast League, the only league where a human with a joystick cannot win against the best teams. And he actually won the World Championship with his team using this little idea. Now, our brains are more powerful than plain feed-forward networks. Most people in pattern recognition and machine learning are using feed-forward networks, especially recently these deep ones that are turning out to be really, really successful in many applications. And I think we will see lots of additional good results using these deep networks. However, all of these deep networks and all of the feed-forward networks are limited if they do not have recurrent connections that allow them to store previous things that you saw in the sensor input. You guys, you all have a recurrent neural network here, which is a general computer, which can compute anything that this computer can compute, and which can devise internal variables for storing things that happened 1,000 time steps ago, and use these things, these memories, plus the current input to do something reasonable, to solve tasks. And these recurrent neural networks, the artificial recurrent neural networks, also can do this. And they also have a long tradition. The first of them appeared at the end of the 80s, and they also have several fathers like Williams and Robinson and Verbos. But the first ones didn't really work so well because they had various problems, which I'm not going to bore you with. However, what you can do is you can use them as prediction machines or as compression machines, as we need them for our curious systems and creative systems. And there's a way of training or changing all these synapses of the networks, of these recurrent networks, such that they become better at predicting or compressing or classifying the data sequences that you feed in. And they can learn, especially the new ones that we have developed, they can learn to bridge long time lags between relevant events. Things that happened 1,000 steps ago may still have an impact on computations that are then done in response to inputs that come 1,000 steps later. So these recurrent networks, they can learn arbitrary programs, essentially. The program is the weight matrix, the synapse matrix. They can learn arbitrary programs. Well, they can implement arbitrary programs, and whether they can learn these most useful programs, that's another question. However, in many recent applications, they outperform now all other methods on interesting tasks, like, for example, connected handwriting recognition. Connected handwriting is much harder than simple digit recognition because nobody is segmenting your data stream. I once knew a guy, do we have some? Yeah, here. I once knew a guy whose name was Mumen Chance, and he signed his name like this. So that here was a U, you see, and that's an M, and that's an M, and that's an E, and that's an N. Right? So it's really difficult to solve that. And there are competitions in connected handwriting recognition, and we are, especially Alex, my postdoc, is always winning them now because these recurrent networks, as they are processing these connected data, what they can do, you can force them to maximize the probabilities of the labels, teacher-given labels, on a training set, where the teacher does not know where exactly does this letter start and where does the next one begin. So the teacher does not know the segmentation of the whole thing. However, at least he knows what is the supposed meaning of the whole thing. And then you have lots of examples like that. And then the thing maximizes the probabilities of these labels on the training set, given all these many sequences in the training set, and then of course you test it on the test set. And one of the competitions that that were won was the one on Arabic handwriting recognition, although none of us speaks a word of Arabic. This is very, very simple stuff in principle. It's much simpler than many of the previous systems that use combinations of hidden Markov models and other feature detectors and combinations of classifiers and all kinds of things. This is working on the raw input. Image input, or in online handwriting recognition, the measurements that you get as you are writing, as the test subject is writing. How much more time do I have? Oh, you just woke up, I'm sorry. 10 minutes, okay. All right, so I wanted to make this connection to this consciousness discussion that we had yesterday. And I don't have much to say about this unity of consciousness thing. However, I think I know where the very symbols that are sometimes conscious and sometimes not conscious, where those are coming from. They are just a natural byproduct of compression. As you are using your recurrent network to encode the history, the data history, which is getting longer and longer, the most natural thing to do for the network, as it is learning, is to set apart a couple of units for certain things that frequently reappear. So maybe some subsequence reappears all the time, which means that it's really efficient for the network to have a few neurons just for that, which are active whenever this thing is present. And as long as you need it to predict the future, for example, or as long as it is sometimes useful to predict the future, to the extent that it's useful, it will appear. And all these, I never really understood this distinction between subsymbols and symbols. You get in these networks, you get on the in the periphery of the network, you get the very simple feature detectors that everybody knows in vision, like on-center of surround detectors, bar detectors, moving bar, orientation-sensitive bar detectors, and all these things. And deeper in there, you get more complex things, that stand for certain spatial-temporal events. And of course, as you are interacting with the world and processing all the data with this general computer, a recurrent neural network, there is one thing that is present whenever you are doing something, which is yourself, the agent yourself. So it's really efficient to have an extra few neurons dedicated to this sort of self-symbol. Like it's efficient to have all things that frequently reoccur be encoded in some sort of prototype, a prototype template or something, such that you, as the new data is coming in, you just need to encode the deviations from the prototype, but not the prototype itself. So it's just a standard question of efficiency to get symbols and subsymbols and self-symbols as a byproduct of data compression. All right, so there are lots of ways of implementing the principle that I explained to you, this dual principle where you need the compression module on the one hand, and then the action selector, which is actually producing the data, or as a physicist, is producing the experiment that leads to the data, or as a baby is producing the finger movements that leads to the data, where there is a regularity that the baby didn't know yet, or that the scientist didn't know yet. Or the artist, which is producing some sort of graphical output, which suddenly falls in place such that it becomes a regular pattern, which is novel, which is not trivial because it looks like all the other patterns that are already known in this type of art. So we need two things. We need this compression machine, the prediction machine, the recurrent neural network, for example, but it doesn't have to be one. It can also be a 3D simulation of the objects that you find in the environment, like this one to the left here. And then you have the other guy, the optimizer of the actions that lead to the data that has the property that you can still discover new, previously unknown regularities. This is a picture of the Icubs that we are currently trying to equip with this principle in the real world. So it's a baby-like robot which is supposed to use this principle of intrinsic motivation to just explore the world and what you can do in it. My take-home message, and I probably still have 2 minutes or something. So I started the talk with these optimal, general, mathematically optimal problem solvers, and there the take-home message is just these things exist, but they are more of interest for theoretical computer scientists, at the moment at least, than for practical roboticists, who are very much concerned about the fact that you have only very few instructions per second that you can use. But how should you use them? Well, you should use them to build a good model of the world and to know how the world works and how your actions in the world can change the world. And even if you don't know how to go to the charging station, it helps, or it tends to help, to acquire all kinds of little problem-solving techniques, which may be as simple as just moving your eyes along a line, which means that your input for a while will be invariant, which means there's a regularity in this input sequence that you get. If you don't even know that, if your compressor is so stupid and random in the beginning that it even doesn't know that as you're moving your eyes along a line, you get invariant inputs, then this will be exciting for a while, and it can learn something there. At some point it will be boring because you don't get any intrinsic reward anymore, because you now can predict and therefore compress. So then you need more complex patterns. Yes, and so this little principle, I believe, is the main reason why we have all these things that the babies do, but also then what later the physicists and the artists and the comedians do. I wish to thank the organizers for their hospitality and for the check which I'm going to spend on my kids. I wish to thank my mom and my dad, without whom all of this would not even have been possible. And I wish to thank my kids, without whom all of this would not have been necessary. And I wish to thank you for your patience.